Hello, this is Tripician, and I will be doing a problem from Chapter 17, Aqueous Ionic Equilibrium, which will be determining if two solutions will create a buffer. The question asks, determine whether or not mixing each pair of solutions results in a buffer. Part A is mixing 15 milliliters of 0.1 molar HF with 135 milliliters of 0.175 molar HCl. Part B is mixing 150 milliliters of 0.1 molar HF with 55 milliliters of 0.15 molar NaF. Part C is mixing 125 milliliters of 0.15 molar CH3NH2 with 120 milliliters of 0.25 molar CH3NH3Cl. We should look at some units and substances that will be important for us to understand to answer this question. We have ml, milliliters, a unit of volume, m, molarity, which is moles per liter, a unit of concentration, HF, hydrofluoric acid, which is a weak acid, HCl, hydrochloric acid, which is a strong acid, NaF, which is a salt of a weak base, sodium fluoride, meaning that when this is in solution, we will be getting a solution with a spectator ion and a weak base. We have CH3NH2 methylamine, a weak base, and CH3NH3Cl methylammonium chloride, which is a weak acid salt, meaning that when this is in solution, we will get a spectator ion and a weak acid in solution. The question is asking if the two solutions for any given part are mixed, would the resulting mixture be a buffer? To understand if this will be the case, we must understand what a buffer is. A buffer is a solution that resists changes in pH when acids or bases are added to it. They can be formed by a solution of weak acid and its conjugate base, or a solution of weak base and its conjugate acid. Therefore, we can say a buffer is a weak plus a weak. However, we must note, both components must be present in significant quantities in order for a buffer to form. What does it mean for each component to be present in significant quantities? To understand this, we should look at the Henderson-Hasselbalch equation, particularly the second part of it, log of the concentration of the base over acid concentration. If the buffer's pH is plus or minus 1 from the pKa, the solution is in the suitable range for the buffer to form. Therefore, the absolute value of this log component of the Henderson-Hasselbalch equation must be less than 1 in order for a buffer to be present. For part A, we are mixing a solution of weak acid with a solution of strong acid. So right away, we know that this will not make a buffer, as the two solutions do not match the definition of a buffer. You can't make a buffer with a strong acid, so no, a buffer will not form. For part B, we must determine whether mixing a solution of HF with a solution of NaF will result in a buffer. The first solution has HF present, which is a weak acid. HF's conjugate base is F-. So, if the second solution provides this component, a buffer could form. The second solution of NaF has the salt NaF. The salt NaF dissociates completely in solution into Na plus aqueous and F- aqueous. Na plus is a spectator ion, so it will not react or change the pH. F- is in fact the conjugate base of HF, and it is provided. So therefore, a weak acid and its conjugate base is provided in the mixture, so a buffer could form. But now we must check if the components are present in significant quantities. If the absolute value of the log of the base concentration over the acid concentration is less than 1, then there is enough of each component to form a buffer. Thus, we must find the new concentration of each component in the mixture. To do this, we have to find the number of moles of base, right here, and divide that by the new volume of the whole mixture, and we get 0.040 molar. We do the same thing for the acid, finding the number of moles of acid initially present, and then divide that by the total new volume of the mixture to get 0.073 molar concentration of acid in this new mixture. We then add these values into the log of the base concentration over the acid concentration and get the value negative 0.26. The absolute value of this is less than 1, so therefore the mixture is a buffer. In part C, we are mixing a solution of CH3NH2 with a solution of This is a weak base, whose conjugate acid is CH3NH3+. So we must ask, is this present in the second solution? In the second solution, we have the salt CH3NH3Cl. When this dissociates, we get a Cl- as a spectator ion, and we do get CH3NH3+. Therefore, in the mixture, a weak base and its conjugate acid will be present, so a buffer could form. However, once again, we must check if the components are present in significant quantities to safely say that the mixture will be a buffer. If the absolute value of the log of the base concentration over the acid concentration is less than 1, there's enough of each component to form a buffer. So we must once again find the new concentrations of the base and the acid in the mixture. When we do this for the base, we end up getting a new concentration of 0.077 molar. And when we do this for the acid, we get a new concentration of 0.12 molar. Plugging this in to the log of the base concentration over the acid concentration, as you can see right here, we get 0.20. The absolute value of this is less than 1, so a buffer will form. In summary, to determine if two solutions will create a buffer, you must first identify if the resulting mixture will contain a weak acid or base and its conjugate. Then, you must analyze if each buffer component is present in relative proportion so that the pH change is plus or minus 1 from the pKa. This is determined by seeing if the absolute value of the second term of the Henderson-Hasselbalch equation is less than 1. That is, the absolute value of the base concentration over the acid concentration is less than 1.